So 5.1, introduction to integration. So the goal, or at least what seems like it's the goal for now, is to find signed areas under curves. So you've got some curve, right? You've got some curve like this, say, and you want to find the area that's under this curve, right? So what's the area of this thing? And you count the ones below the axis as below the x-axis as negative areas. So there's a sign signed to the area. These guys are counted as positive. These are kind of negative, right? And you want to figure out what's the total area under this curve. Okay. And the idea is just the same idea that we've been using over and over in calculus, that the unknown can be analyzed as the limit of the known. Okay. The unknown can be analyzed as the limit of the known, right? If you want to know the instantaneous velocity, something which doesn't make any sense, right, then you can take the limit of average velocities over increasingly short time intervals, right? Here, the idea will be this, that somebody gives you something and says, what's the area under that curve? Okay, the idea will be to say, I don't know, but I do know the area of a rectangle. Okay, right? I do know the area of a rectangle. Right? Just like you could say, I don't know the instantaneous velocity, but I do know the average velocity over a time interval. That's something very simple. Here you've got something very simple. I know the area of a rectangle. Right? So you take a bunch of rectangles that are somehow close, right? Some sort of approximation to the thing that you're looking for, right? And then you take another set of rectangles that maybe is a slightly better approximation. You take a finer approximation to your area, and each of these things is something that you can calculate, right? Because you know how to calculate the area of a rectangle, and you know how to add, right? And here, you're just doing the same thing. You know how to calculate the area of a rectangle, and you know how to add, and this one is a little bit better. And so you take the limit, right? You take the limit as your approximation gets arbitrarily fine, right? And that thing we're going to take to be we'll take to be the area under the curve. Okay, so the area under the curve, something you don't know, will be obtained as the limit of the sums of these sums of areas of rectangles, things which you do know. Okay, so yeah, and some of you know the punchline, right? There's something remarkable that happens, that the area will turn out to be the difference of any antiderivative of the function at the endpoints. Okay, that is, somebody gives you some function, right, and says, what's the area here? It will turn out that all you need to do is find an antiderivative. Find any antiderivative, evaluate it here at one end, and evaluate the antiderivative at the other end, and take the difference. And that will turn out to be the area. Okay? And that's the fundamental theorem of calculus. Okay? So that's how differentiation and integration tie up. Okay, so that will be like the high point of the course, basically. Okay. Okay. So okay. So let me go backwards. Okay. So to talk about integration, we're going to need something called summation notation. Summation notation. Okay. Okay. So if I write something like this, a sub I equals m to n. Okay, where m and n are integers, and right, and okay, m and n are integers. Okay, what I mean by that is that this is the sum a sub m plus a sub m plus 1 plus a sub n. Okay, so I guess I should say you start off with some sequence. Okay, you start off with a sub I sequence, right? You start off with some sequence, and somebody writes this. What does it mean? It means that you take the mth guy. Oh, I don't need to say this anymore. Yeah. You take the sum of a sub m through a sub n. Okay, so that's what that means, right? So like if I so for example, if I wrote a sub I is I squared. So you have some sequence a sub I squared, and I write you're looking at the sum, and I equals 3 to 7 of a sub I. Right. What I mean by that is that you're going to take a sub 3, a sub 4, a sub 5, a sub 6, and a sub 7. Right? In other words, 3 squared plus 4 squared plus 5 squared plus 6 squared, 6 squared plus 7 squared. So that's what that means. Okay. This I is just is what's called a dummy index. This I here is called the dummy index, or just the index. Yeah, Joe.
So your first sum AI, you're not being multiplied. I is just indicating.
It's a subscript, isn't it?
It's a subscript. Yeah, so it's just like in this. Remember when we talked about sequences? We said they're really functions. You can think of it as a of 1, a of 2, right? Down here, right? I've got here my function is a sub I is I squared. So a sub 1 is 1 squared, a sub 2 is 2 squared, a sub 3 is 3 squared. And you remember back when we talked about sequences, we said that really it might be more proper to say it like this: a of 1 is 1 squared, a of 2 is 2 squared, a of 3 is 3 squared. Because you can think of these as functions, right? But usually when you're writing sequences, you don't write it a of 1, but a sub 1.
It's just hard to tell that it's a subscript. Or no, for the first one, it's just hard to tell.
This one.
Yeah.
Look at it. Okay, it's a subscript. Okay. No, sorry. Okay, we're dealing with sequences, so if you say something that looks vaguely like this, it's a subscript. Yeah, sorry, that's not a helpful thing to say. I remember that's like there was an Indian graduate student in the University of Chicago who was once invited to teach a class, and he came in and just gave this really rapid lecture, and somebody said, "Please, can you talk a little slower?" And he said, "Listen faster." Okay, so some other examples. Regarding the dummy index, if I wrote summation j from 1 to, from 3 to 7 of a sub j, that would mean, of course, the same thing, right? We're just taking a sub 3, a sub 4, up to a sub 7. Okay. So even if the sequence is specified as a sub I, if I write a sub j, it still means this. You can use whatever subscript you like here. You don't have to use the same subscript that you use here. It's just a dummy. Index. Okay. Some other examples. If I write something like summation I equals 1 to 100, right? Then what I mean by that is, what do you think that means? Yeah, it's just going to be 1 plus 2 plus 3 plus 100. Right. Here the you could write this as summation a sub I, where a sub I is I, where you've defined a sub I as I. But this is sort of an abbreviation. Instead of writing that all out, you just write summation of I itself. Okay. Right. If I write summation I squared, right, then that would be the sum of the squares. Right. If I write summation n equals 1 to 100, 1 over n squared, then it's going to be 1 over 1, 1 over 2 squared, plus 1 over 100 squared, etc., etc. Okay. Okay. Does anyone know the sum of 1 to 100 offhand? Is anyone familiar with the formula? There's some formula for the sum of numbers from 1 to n. So there's a formula. If you take the sum of numbers from 1 to n, it actually turns out to be n plus 1 and 2. And there are formulas for sums of squares, sums of cubes, etc., etc. There's actually a famous story related to this sum of numbers from 1 to 100. It's that when the mathematician Gauss was 8 years old or 7 years old, he was in class, and the class was particularly noisy. And so the teacher said, okay, everybody shut up, just spend the next however many minutes summing all the numbers from 1 to 100. Right? And so the kids all quieted down and started doing their sums. But Gauss wasn't writing anything and just sat there and looked up, just thinking. And then after a minute, he wrote down 50-50, and then handed it in. And so apparently he had worked it out in that minute, how to sum the numbers from 1 to 100. Or it could be the following, that he saw that if you add the first and last numbers, you get 100. Right? And if you sum the second to last and the second to last numbers, you get 101. Right? So you get 101, 101, and you get that 50 times. Right? And then he added up. He did that in that 1 minute. Okay. And then, later became the greatest mathematician of all time. Yeah, this story actually, contrary to my other stories, unlike my other stories, this story is apparently true. And Gauss was said to have told it when he was an old man. Hey, when I was a young man, I did this when I was 8 years old. Yeah, those of you who know what an abacus is, it's actually an exercise that people do to sum numbers from 1 to 100 on an abacus. So, but you can avoid that. Okay. Yeah, so there are a bunch of formulas actually. There are some formulas for sums of numbers. There are some formulas for sums of squares. Let me put this one out also. And plus 1, 2, 6, etc., etc. There are formulas. I'll go ahead. Okay. Okay, so okay, so here's what we're going to do to try and figure out the area under a curve. We're going to use something called the right-endpoint approximation. Okay, and so here's the idea. You start off with your curve, right? Somebody says, please find the area under this curve. And what you do is the following. You say, well, you're going to divide AB into n subintervals. Okay, so let's actually, we should call this properly the nth right endpoint approximation. Okay? So, if it's the second one, you're going to divide the base into 2 intervals. If it's the third one, you divide the base into 3 intervals, etc. Okay? So you divide the base into n subintervals of equal length. Right? What's the length going to be? Well, right. What's the length of the total interval? B minus A, right? So of equal length, where the length is denoted delta x, equal length delta x, which is of course B minus A over here. Okay. Let's notice something. Okay, yeah, so let's divide this into n. So we divide this thing into n pieces, right? And we call each point xi. So x0, x1, x2, x3, blah, 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 all the way up to xn. Okay, so x naught is a, right? X1 is a plus delta x, right? So xj is going to be a plus j times delta x. You just add on delta. You add x sub j is xj is your dummy, is again a dummy variable. So x sub 1, for example, would be a plus delta x. A sub 2 is going to be a plus 2 delta x, right? X sub 2 is a plus 2 delta x. X plus 3 is a plus 3 delta x, etc. And we call this collection of points, this ordered collection of points, the uniform partition of AB of order n. Uniform partition. Okay. And then we call summation f xj delta x from j equals 1 to n the right endpoint approximation, the nth right endpoint approximation of the area under F on AB. Okay. Okay. So, what is that thing? Let's take a look at what that is. Right? Summation, what is that? What is that? The summation xj delta x j equals 1 to n. Okay. So, right, so let's say that n is 4, right? So you've got x0, x1, x2, x3, x4 in this picture, right? So what is that thing? You're taking f of x1 delta x plus f of x2 delta x plus f of x3 delta x plus f of x4 delta x, right? Right. So what is that? You see that you take each. Take a look. Okay. You say that you take each interval and you take the right endpoint, right? And you evaluate it. You evaluate it, and then you multiply by the width of the interval, right? So that's the area of this rectangle, right? And then you do that for the next interval. You do that for each interval, right? You go there, take the right endpoint, evaluate, and then multiply by the width of the base to get the area of this rectangle. Right? And so you get an approximation based on these choices. Any questions on that? Yeah, Rachel.
Is there a left endpoint approximation?
Yeah, certainly. So you could, if you felt like it, you could say, let's take x of j to be this, and then that would be the left endpoint. Right. So, yeah. So you should say it's a bit arbitrary to choose the right endpoint. Why do we have to choose the right endpoint? Why not choose the midpoint? Why not choose some random point? Right. What happens if you choose some random point? Does it change anything? Okay. But in any case, this is called this is one choice. It's called the right endpoint approximation. And maybe let's do a couple of examples. Yeah. Okay, so just a simple one. So let's say that you go from 1 to 5, right? And f of x is x, and let's do also 1 to 5. 1 to 5, and f of x is going to be x squared. So 1 to 5. F of x is x squared. So I'd like you to write down the fifth right endpoint approximation for each of these guys. I'm sorry, they both should be from 0 to 5. Thank you. Okay, turn to somebody next to you and say what you're doing, even if you haven't finished it. Yeah. Yeah, well, because it's the fifth, you're going to use 5. Yeah, yeah, it's specified. Yeah, if I'd said the 10th, then you'd have to divide it into 10 subintervals. Okay, so what do you do? What do you get? You take this thing, you divide it into 5, right? 1, 2, 3, 4, 5. Right. And so what's the sum going to be? What am I going to write down as the fifth right endpoint approximation? I'm going to take f at 1, right, and then multiply that number. So I get f at 1 times the width of the base. Right? Well, the width of the base is 1. Right? F at 2 times the width of the base plus f at 3 times the width of the base. F at 4 the width of the base. And that's right? And then for the first one, of course, that's going to be just 1 plus, right? F of 1 is 1, f of 2 is 2, f of 3 is 3, f of 4 is 4. So for this guy, right? So for number 1, it's going to be 1 plus 2 plus 3 plus 4 plus 5 plus 15, right? And for the second one, we're going to get 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, whatever that is. Okay. And so this would be this number, right? This number is going to be the fifth right endpoint approximation of the area. This number is the fifth right endpoint approximation of the area here. Okay, that's the fifth one. Right? If I'd said the 10th one, right, then you have to do this in the partition of 10, right? So you'd say 10th approximation. That would give me, right, of course, f of a half times a half plus f of 1 times a half times plus f of 3 halves times a half plus all the way up to f of 5 times a half. Right? So that would give me 1 half plus 1 half squared plus 1 half plus 3 halves plus etc. Up to 5 for the first one. And then for the second one, I get a half squared times a half plus 1 squared times a half plus 3 halves squared times a half plus 5 squared. Okay. So these would be the 10th right endpoint approximations. Yeah, sure.
So when you were doing it for the fifth, where did you get the 1 from, and where did you get the half from when you were doing it to the 10th?
Well, think of what it is, right? You have to take the value of the function at the right endpoint and then multiply it by the width of the base. Right? Here's the value of the function. Here's the width of the base.
Yes.
Here in the 10th one, here's the value. The function is going to be. Now we divide this thing into 10 parts.
Oh, so it's still 0 to 5, it's not 0 to 10?
No, right, from 0 to 5. So, so this is the thing that we're approximating. We're not changing what we're approximating. We're changing the fineness with which we approximate. So, for the 10th one, you divide the base into 10 parts, and then you'd evaluate at each point and multiply by the width of the base. The width of the base is now a half, right? And that would give you a better approximation of what the of what the area is. Right? The first one is crude. Right? The first approximation is crude. Right? First approximation is crude. Second one may be a little better, or maybe it's the same. Right? No, it's a little better. Right? And then the third one is a little bit better. As you get finer, you might imagine, maybe you can imagine that it gets better. Okay. Okay. So this is how we are going to define area, and this is not really a great definition of area, but this is how we're going to do it. So given a continuous function on some interval, and let's say that it's positive. Some non-negative function. The area under the curve is defined as the limit of the. What you do is you take the nth right endpoint approximation, and then you let n go to infinity. Okay. So where this thing here is the nth right endpoint approximation. So let me give you one example of how that's done. So here's an example. Somebody asks you for the area. So here is, say, the x squared function again, and you're going to go from 2 to 6. Somebody asks you for the area between 2 and 6 on the function f of x equals x squared. So you basically do what you did before, but just in a more abstract way. You say, okay, well, I'm going to divide this thing into n pieces, right? So divide 2, 6 into n pieces and subintervals, right? Each of length delta x being 4 over n, right? 6 minus 2 over n. Okay. Then, as before, x of j is going to be the left endpoint plus j times delta x. Right? A plus j delta x. Right? X of j is this, as j ranges from 0 to n. Right? And so we can write down the nth approximation. The nth approximation is then summation f at xj delta x, as j ranges from 1 to n. Right? Which is xj squared, right? I'm taking xj and putting it into the f function, right? F says square what you get, right? Square what you get. And then I'm going to multiply that by delta x. Delta x was 4 over n. Oops. So then we can calculate. We can start to calculate that. So, okay, that's summation of j equals 1 to n of this thing squared times 4 over n. Right. So let's square it. What do you get? Four plus what? 16j over n plus this thing squared, right? What's it squared? 16j squared over n squared. Everything times 4 over n. So let me write that in here. Summation 16 over n plus, well, let me erase this one. I'll just keep it as is. 4 plus 16j over n plus 16j squared over n squared. Everything times 4 plus j minus 1. Okay. Okay. So, okay. So let's break this thing into parts. Okay. So we're taking this. I'm going to write this as 3 different things. So sorry. Let me. I'm going to write this in 3 different parts. So 16 over n plus sum 64j over n plus sum 64j squared over n squared, n cubed, sorry, n squared. Everyone all right with that? I'm summing these things as j ranges from 1 to n. I'm just going to take this as 3 separate sums, right? The 3 separate sums will give me the sum of the 3 things. Right? Okay. So this is as j ranges from 1 to n, as j ranges from 1 to n, as j ranges from 1 to n. Okay. Okay. So what do you think happens here? What do we get? As j ranges from 1 to n, and we take 16 over n, what do we get? We get 16 over n times. So, what do we get? 16 over n plus 16 over n, blah, 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 16 over n. We do that n times, right? So we get 16, right? So the first guy is 16, right? Because we get, 16 over n times. Next thing that happens, we get this 64 over n squared times j, right? So we get 64 over n squared times 1, 60 over n squared times 2, 60 over n squared times 3, etc., etc. We get 64 over n squared times j times 1 plus 2 plus 3 plus 4 plus 5, all the way up to n. Right? Okay. So we can use our handy formula from Gauss that I erased. Sorry. So summation from 1 to n is going to be n plus 1 over 2. N plus 1. Right? Because we get 64 over n squared times 1, that times 2, etc., etc. Okay.
Can you re-explain
Hmm?
that? I don't understand how you got that.
So here what do we have? We have 64 over n squared times 1. We got 64 over n squared times 2 plus 64 over n squared times 3, all the way up to 64 over n squared times n. Okay.
Okay.
So we factor out the 64 over n squared,
Okay.
and we end up with 1 plus 2 plus 3 all the way up to n. We know what that is. That's 1 n plus n times n plus 1 over 2.
Okay.
Everyone all right? Okay. Okay, and then the last one, same thing. And basically what we're doing is we're noticing that we can factor out the 64 over n squared, right? So here we're going to factor out the 64. Right, so what we did here was basically notice that we can factor out the 64 over n squared and get left with summation of j from j equals 1 to n. Here we're going to do the same thing, factor out the 64 over n cubed, and we get the summation of j squared from j equals 1 to n. Right. And so here we're going to get 64 over n cubed times whatever the formula is, n plus 1, and n plus 1, 2n plus 1 over 6. Okay? Okay. So that number, whatever it is the nth approximation, nth right endpoint approximation. Right? So our right endpoint approximation turns out to be this number here. And what's the area? The area will be the limit of this as n goes to infinity. Okay. So the area under x squared on 2/6 is the limit as n goes to infinity of this nth right endpoint approximation. Right? And you see what you get, maybe. Do you see what you get? We're going to get 16. What happens to this thing as n goes to infinity? What do you get? Does anyone see it? Somebody said it, I think. As n goes to infinity, you've got n squared on top, you've got n squared on bottom. These things basically go to 1. These things go to 1 as n goes to infinity. And you're left with 64 over 2, 32. So you get 16 plus 32 plus, what happens to here? As n goes to infinity, you get $64 over 3, right? Because you get 2, these guys go to a 2, and you get 2 over 6, that's 1 over 3, so you get 64 over 3. Which turns out to be 208 over 3 if you work it out. Okay? So that's the area. That's the area under this from 2 to 6. So 2 to 6. Okay. Hold on for 1 second. So before you go, what's an antiderivative of x squared? 1/3 of x cubed. Okay? Let's take 1/3 of x cubed and evaluate it at the endpoints. Okay? And then take the difference. Take the difference. What do we get? Well, 6 cubed is 216. Right? So 216 over 3 minus 8 over 3. 208 over 3. Okay, so that's what's coming.